Hey everybody, and welcome back. In this section we're going to keep working with the binary representation of numbers, but this time we're going to deal with how negative numbers are stored using the 2's complement. We're going to look at complement addition, which is how processors actually perform arithmetic. We're not going to go terribly deep into this topic, but I want you to understand a little bit about the computer science aspect of how calculations are actually done. So let's get started. Okay, normal modern number storage system use a lot of bits, at least 32, to represent any number. That's an awful lot of ones and zeros for us to work with, so we're just going to use 8 bits so you can see the principle without us getting bogged down in tons of writing. So we're going to use 8 bits, that is to say 8 ones and zeros to represent reasonably small numbers. So as a little refresher here, let's represent the number 74 base 10 using 8 bits. So that means our first step is to write a conversion table of sorts, and there's more than one way to do this conversion. But if we're going to binary, there's our ones place, twos place, 4, 8, 16, 32, 64, and 128. We want to convert 74 base 10. So the largest power of 2 that fits into 74 is 64. That's where our first digit's going to be. And so 74 minus 64, that leaves us with 10. 32 does not fit into 10. 16 does not fit into 10. 8 does fit into 10 one time. So we'll take 10, subtract those 8, and that leaves us with 2. 4 does not fit into 2. 2 does fit into 2. And of course, that leaves us with 0. And there's our binary representation. Now you might notice that we didn't use this front slot. That's what we're going to discuss next. So that's the binary representation of the number 74 in binary. But the reality is, if we want to add or subtract, we need to be able to work with positive and negative numbers. And so we're going to kind of use a simple system here, but there's going to be a problem with it. Here's what we're going to do. We're going to take that front digit, we didn't use it at all here, and we're just going to designate that digit as not being part of the number, but instead making this first digit represent the sign of the number. If it's 0, that means that our number is positive. If it's a 1, that means our number is negative. Now the number we just converted was positive 74, and so that means that we should make this a 0. And in fact, this is the number 74 represented in binary, and we know that it's positive because the leading digit is 0. Here's the problem. That means that if we wanted to represent negative 74, you would think that we would leave these 7 digits the same, but change this to a 1, and it would look like this. We'd have 1, 1, 0, 0, 1, 0, 1, 0, and we would think that that would be negative 74 base 10. Notice that these 7 digits are the same as the ones above it. There's the 74, but it's negative, and so we put a 1 there. But that's a problem. Here's why it's a problem, and here's why we can't do that. You know that if we take 74 and add on a negative 74, the result had better be 0, right? So then that means that that should be true in any representation. But if we represent these in binary, 0 followed by 74 to represent positive 74, and 1 followed by 74 to represent negative 74. If we add those up, we don't get 0. Watch, 0 and 0, that's 0. 1 and 1, that adds up to 2, which we have to put a 0 and carry the 1. There's a 1. 1 plus 1 is 2, which we'll put a 0 and carry 1. Look at, that's not 0. And so apparently the arithmetic does not work out. This number is okay, no problem there. It's the negative version of the number that doesn't work out. And that's why we have to make a little tweak here. Okay, I'm popping my face back in here so I can talk to you directly, and I usually don't do that in the middle of a lesson, but what I'm going to show you is extraordinarily important. Nothing we do for the rest of the lesson is going to make sense unless this makes sense. We don't use just a 1 in front of a number to make it negative. Instead, we use what is called the 2's complement. The 2's complement is an extremely important idea for binary arithmetic. The 2's complement of a binary number is found by changing all the zeros to ones, all the ones to zeros, and then you add 1. It's that simple. So let's take a look at a couple examples of what the 2's complement is, and then I'll show you why it's useful. Okay, so let's take our original number that we were working with, that is to say positive 74. This is our binary representation. We're going to find the 2's complement. So we're going to first of all change all the ones to zeros and the zeros to ones. So that means this number will become 1, 0, 1, 1, 0, 1, 0, 1. And then after that, we add 1. Okay, so we add 1 to that, we get 0, carry the 1, 1, 1, 0, 1, 1, 0, 1. This number right here is the 2's complement. Now, what's so special about the 2's complement? Tell me, is this a positive or a negative number? Well, that number right there, the leading digit, the sign bit we call that, tells you that this number is negative. And in fact, you know what number this is? You may guess that is negative 74 base 10. The 2's complement of a number is the negative representation of the number. We'll say that again in just a minute. Okay, one more example. 1011, 0111 base 2. That's our original number. And I'm not even going to tell you what that number is. You could figure it out. But we do know that it's negative, right? Because the sign bit, that leading digit, is a 1. So we know that it's negative something. Let's find the 2's complement. So the 2's complement, we're going to switch all the ones to zeros and the zeros to 1. That becomes 0, 1, 0, 0, 1, 0, 0, 0, base 2. And now we're going to add on 1 to that, which is pretty easy. And we get 1, 0, 0, 1. There's the 2's complement. Now, is the 2's complement positive or negative? Well, since that's a 0, this number must be positive. Let's figure out what this number is. We've got a 1, 2, 4, 8, 16, 32, and 64. 1 plus 8 plus 64, that means this number is positive because of that 0, 73. Now, this was its 2's complement. 2's complements are always 2's complements of each other. That is to say, if we take the 2's complement of this new number, we'll get right back where we were. That means our original number, since it was negative, must have been negative 73 base 10. And so what we just showed is that the 2's complement of a number is the negative representation of a binary number if you have a limited number of bits. Why? Well, for two reasons. First of all, the sign bit is opposite. We saw that right here. These two numbers have opposite signs. The bottom one was positive, but the top one was negative. But the second reason is the more important one. If we add a number to its 2's complement, we will get 0. Let's take a look right now. Okay, we started just a minute ago with this number negative 73 base 10, and then we found its 2's complement, and since it was positive, that means it must be the opposite sign, but the same number. This is positive 73. Now we know negative 73 plus positive 73, that should be base 10, should add up to 0. So here we go. Let's add these up. 1 and 1, that's 2, which means we have to put a 0 and carry a 1. 1 and 1, that's 2, so we'll put a 0 and carry a 1. That's 2. 0, carry the 1. 0, carry 1. 0, carry the 1. That's 2. 0, carry the 1. That's 2, or 0, carry the 1, and we get 0. Now you might say, well, wait a minute, we need one more spot. That's true, but we're only using 8 bits, so anything that happens in that 9th bit, we can just throw it away. After our 8 bits are done, we don't care about anything beyond that. And look at that, we got 0. And so this is the proper representation. And that is the key. The 2's complement of a number is the negative representation of that binary number. Okay, and so I'd like you to take a minute now and practice this and make sure you've got the hang of it before we go any further. I'm giving you 5 numbers there on your screen. I'd like you to determine how each one of those numbers is stored if you are limited to 8 bits. Go ahead and pause the video, work those out, and unpause when you're ready to see if your solutions are correct. Okay, our first one, 109. Let's set up a binary conversion table like we've done before. 1, 2, 4, 8. Now we're going to stop at 64 because this digit really isn't representing 128 anymore. It's representing our sign bit. And I won't give you numbers anything bigger than that. If we had numbers that were too big, we'd need more digits, but we're just limiting ourselves to 8. So the number in question is 109. 64 fits in there, and in fact it fits in one time. So if we subtract that, we're left with 45. 32 fits into 45 one time. That leaves us with 13. 16 doesn't fit in there, but 8 does, and that leaves us with 5. 4 fits into 5, and that leaves us with 1. And so there's our binary representation for 109. Now 109 is shown was a positive number, so that means we should go ahead and put in a sign bit of 0 since it represents positive. And there we are, we got it. That is 109, positive 109, that is, base 10. Now as long as we have that, we should represent negative 109. Remember, we can't just flip this. What do we need to do to find negative 109? We need to take the 2's complement, so let's do that. First, we're going to switch all these 1's and 0's over, so this becomes 1, 0, 0, 1, 0, 0, 1, 0, flipping all the 1's and 0's from 109. Now we're going to add 1 to that, and if we do that, we get 1, 1. From the right, 1, 1, 0, 0, 1, 0, 0, 1. There it is. That is our 2's complement. This is a negative number since the sign bit is now changed, and because that is the 2's complement of 109, that means that that is negative 109. Now before we leave that, what would we get if we added that 8-bit binary number and that 8-bit binary number? Well, if we added those together, and you can check it yourself, those would add up to 0 because 109 plus negative 109 is 0. Okay, how would we represent negative 1 base 10? Well, we don't know. First, we'd have to start out by representing 1. So in order to figure out what negative 1 is, let's figure out what 1 is. 1, base 10, in binary, that's pretty easy. It's a positive number, so we're going to have 0 in our sign bit. And then it's just 1, so that's going to be, the first 7 digits will be 0. That is to say a sign bit plus 6 zeros and 1. There's our 8 bits. And so 1 base 10 is 0, 0, 0, 0, 0, 0, 0, 1 base 2. Now what's negative 1 going to be? Let's find the 2's complement. So if we go ahead and find the 2's complement of that, it is 1, 1, 1, 1, 1, 1, 1, 0. Now we flipped all the zeros and ones. Let's add 1. And we get, that one's pretty easy, 1, 1, 1, 1, 1, 1, 1, 1. Now that's a negative number, and in fact that is negative 1. Now you might say, well, that's a really, really big number. That's not a really small number. And in fact, we know that this is negative 1 because if you add 1 to negative 1, you'll get 0. And if you add 1 to this digit, you'll get a bunch of carrying, and these will become 0. What about 0? Well, that one's pretty easy. 0 has a sign bit of 0. We consider that to be a positive number. And we're going to follow that by 7 zeros. And so 0 base 2, or 0 in binary, is just 0, 0, 0, 0, 0, 0, 0, 0. Now we've answered the question, but it is interesting to say, what would negative 0 be? Negative 0, well, if we want the negative version of a number, we change all the zeros to ones, ones to zeros, and add 1. So negative 0 would be found by taking the 2's complement, which would be 1, 1, 1, 1, 1, 1, 1, 1, and then add 1 to that to get the 2's complement. And if we do that, we get 0, 0, 0, 0. You get the idea. And of course, anything beyond that 8th digit we don't care about. And so negative 0 is exactly the same as 0. No surprise there, just to show that our number system seems to be stable here. Finally, negative 42 base 10. What's that going to be in binary? Well, we don't know, but let's start by finding 42 base 10 in binary using 8 bits. So let's make our conversion table. 42 positive, we're going to have a 0 in that sign bit. 42 is the number we're trying to convert. 64 does not fit into 42, but 32 does. So 42 minus 32 leaves us with 10. 16 does not fit into 10, but 8 does. 1 time, that leaves us with 2. And so 42 using 8 bits is 00101010. Now how do we get negative 42? You got it. We're going to take the 2's complement. So let's take and switch all those zeros to 1s and 1s to 0s. And then we're going to add 1 to that. So this number down here, that is the 2's complement. Specifically, it's the 2's complement of 42, and therefore it's also negative 42. We know it's a negative number because our sign bit turned out to be 1, which is negative. Okay, let's go the other direction. What negative numbers are each of these three 8-bit values representing? The thing to note here is that all three of them have a sign bit of 1, that leading digit's a 1, and therefore we know that these are negative numbers. So to figure out what they are, we're just going to take the 2's complement to find out what number it is. So we don't know what that's worth, but let's take the 2's complement. The 2's complement will be 001000100, but we got to add 1 to that. Okay, so what number is this? That's the question. Okay, in binary we have a 1, no 2's, a 4, no 8's, no 16's, and a 32 right there. So if we add those up, we get 36, 37. This number is 37. We know that it's positive because of the 0, and since this is the 2's complement, then it must have been representing originally the number negative 37. Know that this was a negative number, but we can't tell what it is. We can't convert that directly, so we find the 2's complement. The 2's complement is 37, and the 2's complement is always the negative representation, so our original number must have been negative 37. The second one, B. 10000001. Okay, we don't know what that number is, but we do know that it's negative something. So negative what? Well, let's take the 2's complement to figure out what the opposite sign version is. So that'll be 0, 1, 1, 1, 1, 1, 1, 1 when we take the 2's complement. So this is our 2's complement. That tells us this is a positive number. And we can add up all these binary values. 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. And that equals 127 in base 10. And therefore our original number, since this was the 2's complement, must have been negative 127. Okay, I'd like you to do C. Tell me what negative number 1111 is representing. Okay, here we go. The sign bit is 1, and so it's negative something, but negative what? Well, let's take the 2's complement here. Flip all those 1's to 0's, and then add 1. And of course we get 1. So this number is 1 base 10, and that's the 2's complement, so our original number must have been negative 1. And actually we saw that in a prior example. Okay, rewind those. Tricky stuff, but now we're ready to do some adding and subtracting. Okay, and now that we have all the information about how numbers are stored, whether they're positive or negative, we can actually do some binary arithmetic here. So let's do a simple example. Let's take 72 base 10 and add 17 base 10 to that. So I'm going to save some time and tell you what these binary representations are. 72 base 10 is 01001000, and 17 base 10 is 00010001. So if we want to add those together, we can go ahead and do that pretty easily. Now both of those numbers were positive numbers because their sign bits were 0, and we get a positive number because the sign bit is 0. And what positive number is that? That's 1, no 2's, no 4's, 8, 16, no 32's, and 64. And if you add those up, you get, no surprise, 89 base 10. Now that's a pretty easy case because they were positive, but let's look at some values where not all the numbers are positive. Okay, our next one, let's add 72 base 10 to negative 17 base 10. That's the same as subtracting off 17. Well, 72 base 10, we already did that in the previous example, so that's going to add up to be just the same type of number. But negative 17 is going to be the 2's complement. So I'm going to go back here for just a minute. Our previous problem showed that 17 was 0, 0, 0, 1, 0, 0, 0, 1. So we need to find the 2's complement of that. If we find the 2's complement, we flip the zeros and ones and add 1. That is the representation for negative 17, and so that's what we'll add on. So this time we're going to add on the 2's complement of 17, which is the same as performing subtraction. Notice that we don't actually have to do any subtraction here. We're getting subtraction performed by performing addition. Here we go. Now there is a carry digit there, but we don't care about that. And so our result is 0, 0, 1, 1, 0, 1, 1, 1. And if you add that up, we get 1 plus 2 plus 4, no 8s, a 16 and a 32. And that adds up to 55, which is exactly what you'd expect 72 minus 17 to be. Now again, we're doing a pretty simple problem in a real complicated way, but the goal here is for you to understand how the processor works. Processor can't actually do subtraction, it can only do addition, and this is a clever way to accomplish that. All right, so let's take a look at a couple of cases where our result is negative. That has a little bit different look. So let's do a real simple case here. Let's add negative 4 and negative 2. Now, of course, we know that the answer of that should turn out to be negative 6, but let's see how this is handled using 8-bit storage and complement addition. All right, so we want to represent negative 4 using 8 bits. We don't know how to do that, but we do know how to represent 4 using 8 bits. So let's start with that. I'm going to go down here and note that the representation of 4 base 10 is 0 because of our sign bit. 0, 0, 0, 0, 1, 0, 0. That's no 1s, no 2s, a 4, and none of anything else. Now if we want to know what negative 4 is, of course we need to take the 2's complement of that. So I'm going to switch that over to 1, 1, 1, 1, 1, 0, 1, 1. I'm going to add 1, and that gives us the 2's complement, which is, of course, negative 4. Okay, so now that we know what that number is, we can make it part of our addition problem. Now, of course, we also need to know what negative 2 is, so we'll give that the same treatment. And so our representation of 2 using 8 bits will have a 0 in the sign bit, a 1 in the 2's place, and 0 everywhere else. Now if we want to find out what negative 2 is, we're going to take the 2's complement, which will flip the 1's and 0's and add 1. And that gives us the representation for negative 2. And we can make that part of our problem. So we have negative 4 represented, we have negative 2 represented, we can add them up. Now if we do that, we get 0, 1, and our result is 1, 1, 1, 1, 1, 0, 1, 0, base 2. But here's the thing, that's a negative number, right? Our sign bit tells us that's a negative number. And when we see that this is a negative number, we know that this isn't our answer, this is the 2's complement. We know that negative numbers are represented by their 2's complement, so we need to switch this back to find out what number it is. So now let's take the 2's complement of this number since the result is negative. We take the 2's complement of that, and we're going to add on 1, and there's our result. We have 1 in the 2's place, we have 1 in the 4's place, which means this is 6, but it was, after all, a negative number, and so our result is negative 6 base 10, which is, of course, what we knew all along, but now we've shown how that's done through addition. Now that's tricky stuff. Pause the video and do the other one up there. See if you can use that same process to add negative 3 and negative 9. Unpause to see if your solution looks correct. Okay, so the representation of 3 has a 1 in the ones place, a 1 in the twos place, and zeros everywhere else. The twos complement will be -3, and this is our result. We can make that part of our problem. The representation of 9 is a 1 in the eights place, a 1 in the ones place, zeros everywhere else. The twos complement of that is shown here, and that is going to be -9. We can make that part of our addition problem. And now we can add those up. And we've got our result. Here again, our sign bit turns out to be negative. That means we need to interpret this number. We can't take it at face value like we can with a positive number. So let's find the twos complement of this. Switch the ones and zeros, add 1, and there's our result. Now we know that this was a negative number because of our sign bit. We have a 4 and an 8. That's -12. And that's our result, which again, of course, we knew it was all along, but now we've shown why. Okay, last problem of the day here. I just want to make sure that you see the difference about when we need the twos complement and when we don't. Let's take 31 base 10 minus 80 base 10. Okay, so we just have to look at each of these numbers. Is 31 positive or negative? It's positive, right? It's not written there, but we know that this is a positive 31. Therefore, this number is going to be a 0 sign bit followed by all the digits that it takes to represent 31. I know that you could figure that out, but that's going to be 0, 0, 0, 1, 1, 1, 1, 1. 1 plus 2 plus 4 plus 8 plus 16 is 31. We do not need to take the 2's complement because that's a positive number. Now subtracting 80, remember that's really just the same as adding a -80, and that's the key. So we can only add, that's the only operation we have. If we want to subtract 80, we have to add a -80. What's -80? Well, I don't know, but we can figure that out. We have to start by finding out what the representation of 80 is. So positive 80 is a sign bit of 0, a 64, no 32s, a 16, and zeros everywhere else. 16 plus 64 is 80. Now we want to know what -80 is, so let's take the 2's complement of that. And there's -80, that is the 2's complement of positive 80. Now that's the next part of our problem. So we're not actually doing subtraction, we're doing the addition of a negative number, which is a 2's complement, shown here. Now we can do our addition. Okay, here's our result. Notice what we got. Is our result positive or negative? Well, our sign bit says that our result is negative. Therefore, we can't interpret this directly. We need to recognize that it's a 2's complement and change it back. So we know that our answer is equal to negative something, but negative what? Let's work that out. Let's take the 2's complement. There's our 2's complement. Now let's figure out what that number is worth. There's a 1, no 2's, no 4's, no 8's, a 16, and a 32. And if we add those up, we get 49. So our number is negative 49, and that is the result of our addition. And in fact, 31 minus 80 is in fact negative 49. So you can see there we only had to switch the 80 to its 2's complement because that was the number that was negative. 31 was positive, we got to leave it. We had to switch our answer by taking the 2's complement because it was a negative number, and negative representations always need to be switched over for interpretation. Okay, well, there's a lot of ones and zeros in that lesson, and we're not going to go any further with this topic. That's definitely enough to give you a sense for how those calculations are done. The first of 3 things that you really need to remember when you do your homework for today, the first one is that we express negative numbers by using the 2's complement. And to find the 2's complement, you switch the ones and zeros and then add 1. The reason that the 2's complement works as a negative representation is because you can add it to its positive version and you will get 0. The other reason it works is that that sign bit will always turn out to be correct. If it's a negative number, there will be a 1 in that leading digit, and if it's a positive number, there will be a 0. And finally, anytime you get a negative result on a computation, because your leading digit, the sign bit, is a 1, then you know that that's a negative representation, and you need to take the 2's complement to find out what that number is. So you know it's negative, but taking the 2's complement will tell you negative what is your result. Okay, that wraps it up. Tricky stuff. Don't hesitate to reach out and let me know if you want to work through a few problems on Zoom. I'm happy to go through a couple of these with you. Good luck.